Welcome to our quantum deep dive. Imagine trying to get a clear picture of something incredibly delicate, maybe something you can barely shine any light on at all. Or perhaps you're trying to see through conditions where light just doesn't cooperate. Think deep space, or maybe thick fog. Standard imaging, the kind our eyes and most cameras do, it really hits a fundamental wall when light is scarce, or when the sample itself is super sensitive.
Exactly. Imaging is absolutely vital across so many different fields: medicine, materials science, astronomy, biology. I mean, the list goes on. But its power is severely limited when the very thing it relies on, light, becomes the problem itself. You either don't have enough of it, or using enough light actually causes damage.
And we're exploring how to break through that wall today. We're guided by an essay called Quantum Imaging, Precision with Weak Light by Jurgo Schneepat. Our mission really is to dive into this essay and uncover how the truly strange, kind of non-intuitive rules of quantum mechanics offers a completely new way to see in these challenging low light or sensitive conditions.
It really is a field that forces a shift in perspective, a big one. You have to stop thinking about light just as, a continuous beam, and start thinking about it as individual quantum packets, photons, and how their fundamental properties can be, leveraged. It's pretty mind-bending stuff, but incredibly powerful when you get into it.
Okay, so let's start by really looking at that wall, that problem you mentioned.
Yeah.
When you're trying to image with very, very little light, what are the core practical difficulties? What actually happens?
Well, practically, you just get images that are incredibly noisy, maybe blurry, or sometimes just blank. Nothing useful. But the essay dives into the fundamental physics behind why that happens at these low light levels. Probably the biggest issue is the quantum nature of light itself. See, at low intensity, light isn't some smooth flow. It's these discrete little packets, photons, trying to measure a picture with only a handful of photons. It's like trying to weigh something accurately with only a few grains of sand, right? So classical intensity measurements, they just aren't sufficient to capture the subtle information each precious photon carries.
Okay, so just not enough packets to build a clear picture.
Exactly. And that leads directly to a terrible signal-to-noise ratio, or SNR. The tiny amount of signal you have, those few image-carrying photons, it's just easily drowned out by all sorts of noise. You've got thermal noise from the equipment, electronic noise in the detector, and even just the inherent randomness when you're counting very few particles. Statistical noise.
Like trying to hear a wisp in a rock concert.
That's a great analogy, yeah. Then you have detector limitations. Our standard cameras, they just aren't built to register single photons efficiently. Now, special single photon detectors do exist, but historically they've been expensive, difficult to use, and often need extreme cooling, not very practical for many situations.
Right.
And finally, there are temporal constraints. To gather enough of those rare photons in low light, you typically need a really long exposure time.
Okay, leave the shutter open longer.
Right. But if your object is moving, even slightly, you get motion blur. And maybe more crucially, for things like biological samples or sensitive materials, that long exposure can actually damage or alter the very thing you're trying to image before you even get a good picture.
Wow, so you could destroy what you're trying to see.
Precisely. So it all raises this important question. How do you possibly get useful information from this tiny signal that's overwhelmed by noise without using damaging amounts of light or super long exposure times?
Okay, so it's not just a little dim. You're hitting a fundamental limit based on how light actually behaves at those tiny levels.
Yeah.
So what does this all mean? How does quantum mechanics step in to solve these, seemingly impossible problems?
This is where the weirdness of quantum mechanics becomes our friend, actually. It offers properties light can have that simply don't exist in the classical world we're used to. And these properties can be used to gain advantages. The essay highlights a few key ones. First, there's quantum entanglement and correlation.
Entanglement. Heard of it.
Right. Imagine you have two photons created together in a special way, so they are linked or entangled. Measuring something about one photon instantly tells you something about the other, no matter how far apart they are. This correlation allows us to extract information with incredible precision, even if the light interacting with the object is super, super weak. It's kind of like having a partner who sees a really blurry image, but because you have a perfect, noise-free view of their linked twin photon, you can reconstruct what that blurry image should look like.
Okay, that's cool. Using the twin to figure out the original.
Exactly. Then there's quantum coherence and quantum illumination. Coherence is basically about waves staying perfectly in sync, maintaining their phase relationship. Quantum illumination leverages this, often with entangled light, to essentially make your signal beam incredibly resilient to noise. So even if the light hitting the object and bouncing back gets completely scrambled by a noisy environment, its entanglement with a clean reference beam allows you to pull that signal out from the noise floor far better than classical methods ever could.
So it cuts through the static.
In a way, yes, it's a huge advantage, especially where noise is just unavoidable, like imaging inside living tissue, for instance.
Right.
And finally, the essay talks about using non-classical light sources. This just refers to generating light that has properties engineered beyond classical limits, things like squeezed light or single photons emitted one by one on demand. These sources can fundamentally reduce the noise in your system right from the start, or even enhance resolution in ways classical light sources like lasers or lamps simply can't.
It's fascinating how these unique quantum properties offer, well, theoretical and practical ways around classical limits that seemed totally unbreakable before.
Okay.
Let's maybe unpack a couple of those core quantum basics just enough so we can really grasp how this weirdness actually helps us see.
Absolutely. Good idea. The essay reminds us of a few foundational ideas that are key here. First, wave-particle duality. You've probably heard this one. Light isn't just a wave like ripples on a pond, or just a particle like a tiny bullet. It behaves as both, depending on how you look at it, how you measure it. We see its wave nature in things like interference patterns, where waves add up or cancel out.
Right, the classic double slit experiment.
Exactly. And we see its particle nature when detectors click, registering these discrete packets of energy we call photons. This dual nature is really key to many quantum techniques. Then there's the Heisenberg uncertainty relation.
Ah, the famous one. Can't know everything precisely.
That's the gist. It's a fundamental principle stating you simply cannot know everything about a quantum particle at once with perfect accuracy. For example, you can't perfectly know both a photon's exact position and its exact momentum simultaneously. There's an inherent fundamental blurriness.
Which sounds bad for imaging, doesn't it?
Mm-hmm.
You want precision.
You'd think so. But here's the surprising insight. This uncertainty isn't always a hindrance. It can sometimes be used counterintuitively to extract different kinds of information or to structure light in new ways that actually bypass classical limitations. It's a trade-off you can sometimes leverage.
Oh, okay.
And we already touched on quantum coherence and entanglement. Coherence is about waves staying in step, maintaining phase stability. Entanglement, as we mentioned, is that deeper link between particles, like two coins that, no matter how you flip them separately, somehow always land on opposite sides, heads, tails, heads. This linked fate, this correlation, it persists even in noisy environments, and that's absolutely crucial for extracting those very weak signals we're talking about.
Okay, so these strange principles, how do they translate into actual, tangible imaging techniques that researchers are building and testing?
Right, the practical methods. That's where we get to the specific techniques discussed in the essay. One prominent method is called ghost imaging. And this one sounds really wild, almost impossible when you first hear about it.
Ghost imaging. Okay, I'm intrigued.
The principle is definitely counterintuitive. You split a light beam into two correlated beams, often using entangled photons, but not always. One beam, let's call it the object beam, interacts with the object you want to image. But here's the weird part. The detector measuring that beam, the one that hit the object, doesn't actually capture a recognizable image. It just measures the total intensity of light that got through or reflected. No spatial information.
There's just a brightness reading. How do you get an image?
Right. The second beam, the reference beam, never interacts with the object at all, but it carries the spatial information about the original beam's structure. The magic happens when you correlate the measurements from the object beam detector, which has intensity info but no spatial detail, with the measurements from the reference beam detector, which has spatial detail but no object info. By statistically correlating these two sets of measurements over many photon pairs or light fluctuations, you can computationally reconstruct an image of the object. It's almost like the image is a ghost that you only see through the correlations between the two beams. The essay gives the core idea of the correlation calculation used.
So you're literally imaging something by measuring light that didn't interact with it, in a way.
In a very real sense, yes. The information is encoded in the relationship between the beams.
Okay, where would you use something like that?
Applications mentioned include biomedicine for very sensitive samples, where you want to minimize light exposure on the object itself, potentially seeing through scattering environments like fog for security, and maybe low-light astronomy where signals are incredibly faint.
What are the catches? It sounds complex.
It is. The challenge is you need incredibly precise timing and detection to measure these correlations correctly. Single photon sensitivity is often required. And reconstructing the image computationally can take a lot of processing power, which makes it complex to scale up for real-time applications sometimes.
Okay, that's bizarre and fascinating. What about quantum illumination? You mentioned that helps with noise.
Yes, quantum illumination is a technique particularly designed for situations where your signal is going to be completely swamped by noise. Think trying to find a weak reflection off an object hidden in a ton of background light, or through scattering media. It typically uses entangled light. You send one entangled partner, the signal beam, towards the potential target area. It interacts, bounces back, and gets corrupted by all the noise in the environment.
So it comes back looking like useless static.
Pretty much, on its own. But the other entangled partner, the reference beam, or idler, is kept separate, clean, and protected from that noise. Even though the returning signal beam seems uselessly noisy, its hidden quantum correlation with that clean reference beam allows you to perform a joint measurement. This measurement lets you distinguish the very weak signal from the overwhelming noise much, much better than any classical radar or LiDAR system could possibly do.
So it's like having a secret key.
Exactly. The reference beam acts like a secret key that lets you decode the hidden message, the signal, which is buried deep within the noise or static.
Very clever. And the third method involved using those non-classical light sources we talked about earlier.
Right, so instead of just using standard laser light or thermal light, you actually engineer the light itself to have special quantum properties from the get-go. Key examples are entangled photon pairs, which we've discussed. They're often created by a process called spontaneous parametric down conversion, SPDC, basically splitting one higher energy photon into two lower energy linked ones. These pairs are the fundamental resource for techniques like ghost imaging and quantum illumination because their correlation carries information efficiently and robustly.
Okay.
Another crucial source is squeezed light. Now, imagine the inherent quantum noise, the sort of fuzziness present in any light measurement due to its quantum nature. Squeezed light is specially prepared so that this noise is reduced or squeezed in one specific property you care about, maybe the intensity, amplitude, or the phase below the standard quantum limit, the best you can do classically.
Below the normal limit.
Well, it comes at a cost, thanks to Heisenberg's uncertainty principle. If you reduce the noise in one property, you have to increase the noise in the conjugate property. So if you squeeze amplitude noise, phase noise goes up, and vice versa. But if you only care about measuring the amplitude precisely, that's a great trade-off.
Ah, okay. So you choose what to make more precise.
Exactly. The benefits here are significant. You can potentially get an improved signal-to-noise ratio straight from the light source itself. This can lead to higher resolution, which is particularly useful in delicate microscopy. And importantly, these squeezed light sources can often be integrated into existing optical setups, like microscopes, to give them a quantum boost without redesigning everything.
This sounds like really complex physics, moving parts at the quantum level. But the essay talks about actual technological advancements, bringing this out of the pure research lab. What's happening on the tech side that's making this practical?
Yeah, this is where the engineering really meets the quantum concepts, and it's crucial. There's been massive progress, particularly in detection technology. We now have high-efficiency single-photon detectors. Instead of maybe catching only a fraction of the photons that hit them, modern detectors like superconducting nanowire single-photon detectors, or SNSPDs, can catch nearly every single one. The essay mentions efficiencies getting up towards 98%.
Almost perfect detection.
Almost perfect. And crucially, they are also incredibly fast, reacting in picoseconds, and have very few dark counts. Dark counts are false detections, clicks when no photon actually arrived. Low dark counts are vital when your signal is already weak.
So better eyes to see these faint signals.
Exactly. These improvements are absolutely essential for capturing those faint, fast quantum signals accurately. And building on this are the developments in quantum cameras. Now, these aren't your standard camera sensors you find in your phone. They are arrays designed specifically with these highly sensitive single-photon detectors, often capable of timing each photon's arrival very precisely. They're built to capture the quantum properties across an image, not just intensity, but correlations, timing information, maybe even phase.
So they see more than just brightness.
Precisely. They are being developed to directly visualize things like entanglement patterns or capture the subtle noise reduction from squeezed light across a whole scene. This is paving the way for high-resolution imaging that needs almost no light at all.
So if we connect this to the bigger picture, These detector developments are sort of the unsung heroes, making quantum imaging actually feasible outside of these heavily controlled lab experiments.
I think that's a fair way to put it. They are absolutely critical enabling technologies. Without them, many of these quantum ideas would remain just theoretical curiosities.
That brings us then to the big question. How do we take these powerful, potentially complex quantum methods and integrate them into real-world applications? Get them out of the lab and into hospitals or factories.
Right, bridging that gap. The path forward, as discussed in the essay, involves several key aspects. First, hybrid technologies. It's often not about completely replacing everything classical with quantum systems. That might be too complex or expensive initially. Often the most effective approach, especially in the near term, is to combine the two. You use the precision and, say, noise resilience of quantum components where they offer a unique advantage, while relying on efficient and familiar classical systems for other parts of the imaging process.
Like adding a turbocharger to a regular engine.
Kind of, yeah. The essay gives an example of integrating squeezed light sources into otherwise classical microscopes to boost their sensitivity or resolution beyond the classical limit. Best of both worlds. There's also, of course, a strong push for scalability and accessibility. Right now, some of this tech is still expensive, maybe bulky, requires special conditions. So the focus is on miniaturization, making systems portable enough for field use or clinical settings. Reducing costs is obviously huge if these are going to become widespread, and standardizing the interfaces and components is also key so researchers and companies can integrate these quantum capabilities more easily into existing platforms.
Makes sense. You need it to be usable and affordable.
Absolutely. And the essay highlights some really compelling case studies where this is already showing immense promise, even if it's still early days for some applications. In medical imaging, for example, imagine detecting the very early signs of cancer with minimal, non-damaging radiation doses because you need so few photons.
That would be huge.
Or imaging incredibly sensitive tissues, like the retina of the eye, with vastly less light, reducing patient discomfort and potential damage. Or even providing surgeons with real-time, super-precise guidance during delicate procedures by seeing structures classical methods struggle with.
Wow.
And in material science, it means being able to analyze the tiny structures and defects in new materials like nanomaterials or semiconductors with unprecedented precision, understanding surface properties at the quantum level, or even imaging individual quantum dots without disturbing their fragile quantum states.
It's clearly a powerful set of tools, this quantum toolbox, with incredible potential. But what are the remaining hurdles? What are the big challenges, and where do researchers see this heading in the future?
Yeah, it's not all solved yet. Definitely not. There are still significant scientific and technical challenges to overcome. We need more stable, robust, and easier to produce sources of entangled and squeezed light that work reliably outside of pristine lab conditions. Optimizing how squeezed light is generated and then efficiently used in a real imaging system is still pretty complex. And while detectors are much better, the very best ones are still often very expensive and might require challenging infrastructure, like cryogenic cooling to get those ultra-low noise levels.
So practical engineering challenges mostly.
A lot of it is practical engineering and materials science, yes. Also, handling noise and errors remains an ongoing battle. Even with quantum advantages, you're still fighting against fundamental things like thermal noise in the environment, the unavoidable loss of photons as they travel through optical components or tissues, and environmental disturbances, vibrations, stray light that can mess up delicate quantum states like entanglement. So researchers are constantly developing better error correction techniques, smarter algorithms to process the noisy signals, and searching for new materials and designs that are inherently more robust against these issues.
Okay, so still work to do. Looking ahead then, what's the future potential? Where could this take us?
Looking to the future potential, the essay paints a pretty exciting picture where this technology moves beyond spiralized labs towards more everyday applications. Think about maybe one day portable medical diagnostic devices based on quantum sensing that you could use in remote areas or a doctor's office. Or security cameras that can see clearly through thick fog or total darkness, conditions where classical cameras are completely blind. Maybe even future smartphone cameras that could achieve incredible low-light performance or hyper-accurate depth sensing for augmented reality using some of these quantum principles.
Quantum cameras in our pockets.
It sounds like sci-fi now, but miniaturization and cost reduction are the keys driving towards that kind of future. It won't happen overnight, but that's the direction. And finally, there's a huge potential, the essay points out, in connecting with other quantum technologies. There are really exciting synergies emerging. Think about using quantum computing for much faster and more complex image reconstruction algorithms, which are often computationally heavy. Or using quantum cryptography to securely transmit highly sensitive medical or industrial images, ensuring privacy, and quantum communication for sending image data securely over future quantum networks. It's all becoming part of a larger interconnected quantum ecosystem. These technologies will likely boost each other.
That integration really shows how these different quantum fields are starting to build on each other, doesn't it? So just to recap then, quantum imaging with weak light is fundamentally about using these unique quantum properties, things like entanglement, coherence, specially prepared non-classical light, to overcome what seemed like impossible classical limits when imaging in low light or with sensitive samples. And this is being made practical, increasingly so, by incredible advances in things like single-photon detectors and specialized quantum cameras. And it's already showing real promise right now in critical areas like medicine and material science, with a longer-term vision for much wider impact across technology and society.
Absolutely. You've summed it up well. It's a field that's rapidly evolving from, purely theoretical concepts into genuinely practical tools. And it's powered by these technological breakthroughs that let us manipulate and detect light right down at its most fundamental quantum level.
The ideas we've explored today, really guided by the insights from Jurgo Schneppat's essay, they really highlight the transformative potential here.
Yeah.
It definitely makes you think, how might these interconnected quantum technologies fundamentally change how you visualize and interact with the world around us in the coming years? Something to mull over, for sure.
Indeed. Our ability to see the microscopic, the distant, and the hidden, it really feels poised for a dramatic quantum leap forward.
It's been a pleasure diving into this with you. Really fascinating stuff.
Likewise. Always great to talk about this.
And for you listening, thanks for joining us on this quantum deep dive. Goodbye for now.